Let's talk about sinusoidal signals. Sinusoidal signals show up very often in nature. For example, if you look at a single frequency light wave and plot the electromagnetic field strength versus time, the signal will be a sinusoidal signal. Or consider simple harmonic motions. In a simple harmonic motion, when you plot the displacement versus time, the resulting signal will also be another sinusoidal signal. Now, examples of simple harmonic motion would be uh, a spring attached to a mass or a boat bouncing on water. Another interesting example is oscillations in circuits. So these are the circuits, for example, which are used to create carrier signals for your cell phone signals. And these are purely sinusoidal signals. So it's not a coincidence that sinusoidal signals are very fundamental and form the basis for Fourier analysis. Sinusoidal signals are what we consider single frequency signals. Other signals which are periodic but are not sinusoids will be considered to be comprised of multiple frequencies. We will talk about continuous time sinusoids and discrete time sinusoids. Continuous time sinusoids are given as x of t is cosine 2 pi f t plus theta, and these are the discrete time sinusoids. Note two differences. First, in the notation of the signal itself, for continuous time we use parentheses, for discrete time we use square brackets. For continuous time t can be any real number, for discrete time n is only an integer, can only be an integer. And just for convenience also and for clarity, whenever we are referring to continuous time frequencies, we will denote the frequencies with capital letters. And for discrete time frequencies, we'll denote the frequency with small letters. Even though the expressions appear very similar to each other, there are some key differences in fundamental properties of continuous versus discrete time sinusoids. Let's talk about property 1 of continuous time sinusoids. For any frequency capital F, cosine 2 pi ft plus theta, which is the sinusoid of frequency capital F, this sinusoid will be a periodic signal and the period will be 1 over f. To see this, let's consider the definition of periodicity. For a signal x of t to be periodic with period capital T, it should be equal to x of t plus capital T for all values of t. What we can now do is calculate the right hand side of this equation and see if that is equal to the left hand side. Then we have proven that property. So x of t is equal to cosine 2 pi capital F t plus theta. This theta can be anything. That is, the theta can be any real number. If I substitute t plus capital T for t, I get the right hand side. I distribute 2 pi capital F over the addition here, and then I get this expression there. Note that capital T is 1 over capital F. Therefore, 2 pi ft will become 2 pi. For any sinusoid, if you add 2 pi to a certain angle, you'll get back the same value. Therefore, this will be equal to cosine 2 pi ft plus theta, which is equal to x of t, which was the left-hand side. Note that this will be true for any value of t, because 2 pi, if you add 2 pi to any angle, you'll still get the same value. What we just saw is that for any capital F, the sinusoidal signal with that frequency will be periodic and the period will be 1 over f. Second property, if we have f1 and f2 which are not equal to each other, then the corresponding sinusoids will not be equal. That means for any distinct frequency, we'll have a distinct sinusoidal signal, or there is a unique sinusoidal signal associated with each frequency. Now, this may seem obvious, but we will see that for discrete sinusoids, this is not the case. Third property is the rate of oscillation increases with frequency. That means as the frequency increases, we'll have faster and faster oscillations in the signal, and the oscillation and the frequency can increase up to infinity. There is no upper limit, and as long as the frequency is increasing, we will have faster oscillations. We can see this effect using a software demo. This is a MATLAB demo made using MATLAB live scripts. What I'm showing here is the signal x of t is capital A cosine 2 pi f t plus theta. Capital A is 1, theta is 0 in this case, and this I can adjust the value of capital F using this slider here. Right now the frequency is 2.6 and the x-axis is time, this variable t, and the y-axis is x of t. Now if I increase the frequency, as you can see the rate of oscillation increases. That means we'll have faster and faster oscillations as I keep increasing the frequency capital F. Now the slider has a certain maximum value, but I can keep going on until infinity, and the frequencies keep increasing as capital F is increasing. Now let's talk about discrete time sinusoidal signals and see if and how they're different. So a discrete sinusoid, x of n is cosine 2 pi fn. Note that I am ignoring the theta here because even if there's theta, it will be the same, or the properties will be the same. In the discrete case, this sinusoid will be periodic only when f is a rational number. Note that this is in contrast with the continuous time signals, where continuous time sinusoids are periodic for every frequency. A rational number is any number that can be written as a ratio of two integers, and they're denoted by the letter q. To see this, consider the definition of a periodic signal, which is x of n should be equal to x of n plus capital N, for where n is an integer, and this should be true for all small n. What we want to see is if a signal is periodic, then the frequency must be a rational number. So we're going to start with the statement A, saying that such an n exists. So what we are saying is, what statement A is essentially saying is x of n is periodic. Then we will start from statement A, and then we will show that f should be a rational number. X of n is cosine 2 pi of n, and on the right hand side I'm substituting n plus capital N for n, and this is what we get. So for left hand side to be equal to right hand side, then this extra angle here 2 pi of n must be an integer multiple of 2 pi. So then this statement implies that f should be equal to m over n. So note that both m and n are integers. So what we just showed is that we started from this statement saying that, okay, x of n is periodic. Then we showed that that would imply that f is a rational number, right? So what we just showed is that x of n is periodic only when f is a rational number. Let's take a minute to look at the logic here. So let's say this f is a rational number is statement B. What we showed above is if statement A is true, then that implied that statement B is true. If you use the rules of logic, what that means is if statement B is false, then statement A is false, right? So if A implies B, then not B implies not A. I would recommend you to pause here and think about that a little bit and convince yourself that this logic is correct. If this logic is correct, then what we are saying is if f is not a rational number, then x of n is not periodic. In other words, x of n is periodic only when f is a rational number. Property 2. If there are two frequencies f1 and f2 such that f2 is f1 plus some integer m, then the corresponding sinusoids will be equal. To see this, let's start with the left hand side, cosine 2 pi f2n. And I'm going to substitute f2 is equal to f1 plus m in here, and then I get this right hand side. Then I can distribute 2 pi inside the multiplication, and I get this. Since m is an integer and n is an integer, therefore m times n is also an integer. So this extra angle here is an integer multiple of 2 pi. That means you get back the same signal. So cosine 2 pi f2n will be equal to cosine 2 pi f1n whenever f2 is f1 plus some integer. Here is an example. Cosine pi over 2n will be equal to cosine 5 pi over 2n because the frequencies differ with an integer. So I want you to pause the video here, find the frequency for the left hand side, find the frequency for the right hand side, and make sure that they are the difference is an integer. Another point I want you guys to think about is for these arguments to be true, or for if these arguments to be valid, should f1 be a rational number? Property 3, the rate of oscillation increases when f increases from 0 to 0.5 and then starts to decrease from 0.5 to 1. And then after that, it starts repeating because we are stepping by an integer. Now, note that this also means that the highest frequency, discrete frequency, which we can observe is 0.5. And then the same frequency also happens at 1.5, but it's the same signal as 0.5, right? So that's why we say maximum frequency is 0.5 for discrete signals. As in the continuous case, we will look at a software demo to see this. So in this demo, I am showing a stem plot of this signal x of n is a cosine 2 pi of n plus theta. Theta is 0 and a is 1. Now for 0 frequency, when f is 0 and theta is 0, so this is cosine 0 for all n, right? So for 0 frequency, x of n is just a constant signal at 1. Now as I start increasing the frequency, I have to start seeing oscillations. So let's say at 0.1, this is how the signal will look like. They said as you increase the frequency, the rate of oscillation must increase. So let's keep increasing this frequency from 0.1 so to 0.2. As you can see, we'll have faster oscillations. 0.3 even faster, and at 0.5 you see the signal is going from 1 to -1 and then to again to 1 at every step. So at every step it's changing its sign and magnitude from 1 to -1. So now after 0.5, so 0.5 is basically this is the maximum change you can get, right? So one step to another step, it's completely going from 1 to -1. So now if I start increasing the frequency from 0.5, the rate of oscillation starts decreasing. 0.8 further now reduced, 0.9 even smaller, and now that frequency 1 is exactly the same as frequency 0 because they're integer separated by an integer. So frequency 1 is again a constant signal. Now if I start increasing, the rate of oscillation starts increasing. Again, 1.1 is the same as 0.1. So this is also what we saw for 0.1. And the pattern keeps repeating as I go. Let's summarize what we saw so far. For continuous sinusoids are periodic for all frequencies, whereas discrete frequencies are periodic only when f is a rational number. In the continuous case, if we have two different frequencies, they will result in two different sinusoids. In the discrete case, whenever two frequencies are separated by an integer, they will result in the same sinusoids. In the continuous case, the rate of oscillations keeps increasing with frequency f, whereas in the discrete case, the rate of oscillation increases from 0 to 0.5 and then starts decreasing until 1 and then starts increasing and so on. Therefore, the maximum frequency is 0.5.